Hi, I'm Chelsea, and today I'm going to explain the chain rule as well as demonstrate with a few examples. Now, before we start jumping into the examples, let's first see how the chain rule can be useful to let us take derivatives of functions. So, we use the chain rule when we usually have a function that is the composition of two other functions. Just for notation's sake, I'm going to call the function that we're interested in getting the derivative of will be this h of x. Okay? H of x in this case is the composition of two functions f and g. Okay? So h of x is equal to f of g of x. Okay? The chain rule says that to find h prime of x, the derivative of h of x, h prime of x will equal the derivative of f of g of x. So f prime of g of x multiplied by the chain part, so multiplied by g prime of x, the derivative of g. So we're working our way from outside to in. Okay? We're taking the derivative of the outside function of f, and we multiply it by the derivative of the inside function. And as these functions get more and more nested, we'll have more and more derivatives being tacked on. So let's look at a few examples to demonstrate using the chain rule. In this first example, I have h of x will be the quantity x squared plus 1 raised to the 100th. Okay? The function f that we're talking about is a quantity raised to the 100th power, and then the function g is x squared plus 1. So, to find h prime of x, what we'll first do, again working from the outside in, is take the derivative of f prime of g of x. So f of x is this whole thing, alright? And what we can do is use the power rule. So the power rule says take the power out in front. So when we're going to take the derivative, we'll bring the 100 out in front. We'll just leave, I'll put a set of parentheses there for that quantity, and then we drop that power by 1. Now inside, we're going to keep g of x, and again, this thing here is our g of x. So all we have to do is nothing changes inside, we'll just leave that x squared plus 1. You can pretend, you could call this inside quantity y, and then take the derivative f of y, and then substitute it back in, the x squared plus 1, or you again can just use the parentheses. Okay? Now we're not quite done because we have the chain part still left. Because this isn't just a variable, it's a function, we have to multiply by the derivative of what's inside parentheses. So now we're going to take the derivative of this thing here. In this case, the derivative of x squared is 2x, and the derivative of 1 is 0. Okay? If we had, say, another quantity squared in here, we'd have to go in one more time and tack on another derivative to the end. But we can stop here. This is h prime of x. I'm just going to take it one step further. The calculus is done, but just to simplify and make things nicer, I'm going to just multiply 2 by 100, get 200, and bring the x in front, and x squared plus 1, that quantity raised to the 99th power. And this would be our final answer for this example. Okay? Let's look at the second example here, where we have h of x equal to e to the x squared. We're used to seeing e to the x, and we know the derivative of e to the x is just e to the x. But this squared power up here makes this a composite function. So, using the chain rule, we'll get h prime of x. Okay? What I like to do again is pretend that in this case here, this thing is our g of x. Okay? So, copying it down, the derivative of e to the g of x will just be e to the g of x. Okay? And then what we're going to multiply by is the derivative of g of x. Okay? And the derivative of x squared is 2x. again, to rewrite it, we get h prime of x is equal to 2x times e to the x squared. And there again would be our final answer. And that's it, using the chain rule. Now the chain rule can be used, again, as I had said before, for maybe a function composed in a function, composed in a function. It can go on forever. And what you need to do is keep going inside and inside in order to tack on all those derivatives onto the end. So for more information, please visit our website at www.sandersontestprep.com. The link is in the description below. Thank you.